Welcome, everyone. Good to see you all today. We'll give folks another minute to join, but very excited to see you today. This is week 3 of the Wiser Quantum Summer Program. This is our 5th year, and we're very excited this year to focus on optimization problems and give you both a perspective from high-performance compute, quantum computing, and AI. And to bring all of this to life today, we have Dr. Monica Van Dieren joining us. So she's a senior technical marketing engineer at NVIDIA. There she specializes in quantum as well as high performance computing and driving the Q2Q academic initiative. Before joining NVIDIA, Monica contributed to IBM's Quantum Accelerator program, and she also served as a board member of various organizations supporting open source homework platforms. With another, she's an advisory board member where they focus on online 3D graphing calculator. You can guess she has a PhD in mathematical sciences from Carnegie Mellon University, and she brings over 20 years of academic experience at universities such as Stanford, University of Michigan, and Robert Morris University to her work. So join me today in welcoming Monica. We'll have the next hour packed with a great session. And over to you, Monica.
Great, thanks a lot. Okay, I'm trying to share the screen here. So yeah, happy Wednesday, everybody. I'm actually very excited to talk to you today about integrating quantum computing and HPC. In fact, maybe make the argument that this is a must. It's not an option for getting to useful quantum computing. And I'll also introduce you to an example, an optimization problem that you can be working on today interactively with me, but then there'll be much more for you to do later and continue your learning. So one thing that I will be talking about and emphasizing is not just how quantum computing and HPC come together, but how quantum computing and AI also come together. And so the goal is to answer a few questions that you might have about AI and quantum computing. And the first is like, how do you put these two together? And that's with an accelerated quantum supercomputer. So I'll define that and talk about the challenges the industry is facing to get to useful quantum computing, but more importantly, how AI helps address those challenges. And then we'll go through that tutorial that I mentioned earlier, which will be an optimization problem on the max cut problem. We'll use Q2Q. That's our open source platform for accelerated quantum supercomputing. And you'll have many links and QR codes in the slides that you can follow to continue your learning after what we can possibly learn in this very short hour. So before we define an accelerated quantum supercomputer and how AI kind of works with it and GPUs work with it, it really helps to understand what makes up a quantum computer. We sometimes take that for granted. So of course, as you all are part of this program, hopefully by now you'll have some understanding of the difference between bits and qubits. So in terms of what they mean mathematically, but bits on a physical device like your laptop or your cell phone are made up physically of transistors. But quantum computers, we're really in the early days of quantum computation, and there's a race to find out which is the best way to build a qubit. It's not going to be transistors. It's going to be more quantum in nature. It's going to be trapped ions, superconducting transmon qubits, neutral atoms, photonics, or maybe something else entirely different. We're not really sure who the winner is going to be. And in fact, maybe there isn't going to be a winner, a clear winner. It could be that there's the future of quantum computing is a mix and match of different types of qubits for different jobs. Right now, we're in the early days of it, so we really don't know. And so the one thing I want to make clear about NVIDIA's role in quantum computing is that we're not actually building any of these physical quantum computers or processors. We're building GPUs, or graphical processing units, which of course are classical, but we work with almost every quantum computing company to help them accelerate their roadmap with whichever type of quantum computer they're building, whether it be trapped ions or neutral atoms or transmon superconducting qubits. We just connect our GPUs to them to help them out. So this is what it might look like, where we have different quantum processors here on the left-hand side. The golden chandelier you often see in the media depicting a quantum computer, that's the transmon superconducting qubit. We have neutral atoms and trapped ions, other examples. But these are actually, on the left-hand side, these are really just quantum processors. They are storing the qubits. They're not doing any computation yet. In order to run quantum computation and manipulate the information that is stored on those qubits, you have to send a signal to change that information, to do that computation. And that is done with the control unit. So this stack here shows several different control units, Different companies make those. We don't make those, but we work with those companies. And those control units will connect oftentimes with like a copper wire to the physical quantum hardware and send signals like electrical pulses, microwave pulses or laser signals to change the information in those qubits and also to read out the information that's stored in those qubits. So that control unit is necessary to do computation. But that control unit also needs to do things like, or has to handle things like error correction and calibration, because the qubits themselves are very noisy. And in order to get useful information out of them, you really need to mitigate against that noise, whether it's bringing it down by doing calibration constantly as you go through your quantum program that you're running, or running error correction in real time as you're running that quantum computation. Computations necessary to do calibration and error correction often require more compute than what can possibly be inside of one of these control units. And so that's where the GPU comes into play. So the GPU is helping the control unit do error correction and calibration to mitigate against the noise in the quantum hardware. So in order to do a quantum computation, to run a quantum program, quantum circuit, you need actually three things. You need the quantum processor, you need a control unit, and then you need a GPU to do the error correction and calibration. So it's really these two stacks here together that make up a quantum computer, or in this picture here, 3 quantum computers, just to run a quantum circuit execution. So many of the algorithms that you're learning about for optimization happen to be hybrid algorithms. And what we mean by that is that part of the algorithm runs on the quantum computer, but also part of the program runs on the classical computer as well. So there's other GPUs that might be in the system beyond the one that's just doing the error correction and the calibration and control in this middle stack. And so this is really the vision of an accelerated quantum supercomputer, where we have the quantum computer here on the left 2 columns, and then the supercomputing center on the right, where we have a big job that's too massive on whatever type of scale you're looking at for running on a classical supercomputer, and the accelerator, or the quantum computer, helps accelerate part of that task. We don't send the entire job to the quantum computer. The supercomputers still do really good things on the types of jobs that are problems that they're good at solving. So we're going to send part of the workflow to the supercomputer, part to the quantum, and they often have to talk to each other as well. So an accelerated quantum supercomputer is essentially this picture. It's a supercomputer with an accelerated quantum computer there, and that quantum computer also has to have GPUs. Okay, so I did mention that one thing that one use of an accelerated quantum supercomputer, one need for it, is that many of our programs in quantum are hybrid in nature, where part of the job runs on the quantum processor and part of it runs on a classical compute. And this is an example of what that might look like, where you're trying to solve a minimization problem, where you have a cost function. In this case, the cost function is the H Hamiltonian here, and our circuit is very simple. It's just rotations around the y-axis, and we're doing some measurements and then computing the expectation value. And so for different values of theta, we're going to get smaller and smaller expectation values. And the goal of this type of problem would be to minimize it. So what happens is you pick a theta value, I'll run it again, and you run it in your quantum processor, you send it to the accelerated quantum supercomputer, or the AI supercomputer, to pick a new parameter that might improve the result, and you cycle back and forth through this loop until you've converged along a solution. This is the picture or the animation of a variational hybrid quantum classical algorithm. They're very common in quantum computing. We'll look at one of them today called QAOA. Okay, so this accelerated quantum supercomputer is not theoretical. It actually, they exist. They're not as performant as maybe we'd want them to be, but we're building these devices in supercomputing centers across the world with quantum control unit companies and all different types of quantum computing companies as well. They're connected to our GPUs to do the error correction and the calibration and control with something we call NVQ link. And so in order to be able to program in this heterogeneous, so different types of physical devices, different types of QPUs, different types of control units, GPUs, supercomputing centers, we need to have a programming platform that can work in this distributed heterogeneous system, and we call that CUDA-Q. CUDA-Q is based in Python, it's based in C++, but you can program at the Python or the C++ layer. We'll be looking at Python today. We have also a library on top of CUDA-Q that makes programming even easier, so you don't have to program a circuit from scratch going gate by gate if you are working on a common problem like an optimization problem and using QAOA like we'll be doing today. So today we'll show CUDA-QX and CUDA-Q. What makes CUDA-Q very performant for doing simulations of quantum doing simulations of the executions of quantum circuits is QQuantum. That's a layer underneath CUDA-Q. We won't be talking about that today, but if you're really interested in how to run simulations on GPUs of not just quantum algorithms, but also physical quantum hardware, the physical qubits, the physical circuits, the understanding the noise between different qubits on a physical circuit, that's a layer of the stack you might be interested in learning more about later. But again, we're just going to be talking at the top two layers here today. Okay, so this is our vision for an accelerated quantum supercomputer to bring useful quantum computing. We're not there yet. There are several challenges between the noisy quantum hardware that we have today and this vision of an accelerated quantum supercomputer. So these challenges, I already mentioned one of them, is that the qubits tend to be noisy, right? So one thing we have to do, or quantum computing companies have to do, is to build better quantum hardware that's less noisy. And anytime you build anything, whether you build a GPU, a quantum computer, or a car, you're going to not just have an idea and then put it into production, you're going to simulate it on computers to understand how that idea, that design idea that you had actually translates into the physical world. Are there problems with it? Is one design better than another? So you might test out several different designs through simulation before you actually go and build it. So we're working with quantum computing companies to build better quantum processors to help them do the simulation of the designs before they put that next design into production. And in addition, so even if the quantum computing companies, use these simulations that we're allowing them, or that we can accelerate with our GPUs, they're going to still have noise within those quantum processors. You're never going to get rid of noise. So we need to have better error correction and calibration strategies to mitigate against the noise of the qubits in the hardware. And this is where AI comes in. We can use AI to help with the calibration, and we can use AI to as part of the error correction strategy. And in order for those AI models to exist, they had to be trained on data, and a lot of data. The data in the situation is executions of quantum circuits on real quantum hardware. Well, we have a very limited amount of quantum hardware out there, and the amount of time and resources needed to generate the amount of data that you would then need to train an AI model is just too much. So what we actually do is we actually can generate synthetic data by looking at simulations of quantum hardware executions on our GPUs. So we've created a lot of synthetic training data of quantum hardware, noisy circuit executions, and we have then used that to train our calibration AI models and our error correction models. And then quantum hardware companies then go and take these pre-trained models and refine them with just a little bit of their real hardware data and get performant results. Even if we have less noisy qubits and have great error correction, maybe and calibration that's AI assisted, there's still room for improvement in the algorithms that we have today. There are issues with some of these quantum algorithms. They're not as performant as we'd like them to be. So perhaps AI can help us, and we'll see that in the example we're going to work through today. AI can help us take the algorithms that we currently have today and improve them by making them perhaps less susceptible to noise. Maybe they converge to solution faster. Maybe they require fewer gates or fewer number of qubits. So we'll see some examples of how AI is helping us to improve the algorithms. And then finally, we have to put all this together and deploy this in a supercomputing center, and that's what we're working with NVQ Link. So those are all sorts of problems that the industry faces, and each one of these, AI and NVIDIA GPU supercomputing is helping to advance the industry and solve these problems. And so we really need, the GPU to be working with the quantum computer. You can't think of them as separate devices. And another example of how we're not really thinking about them as separate devices and when we're trying to solve big problems is an example that is relevant to although this is a chemistry example, we can learn from it when we look at optimization problems. Optimization problems, we're often trying to find the minimum value. So this is an example where we wanted to find a minimum value of a chemistry problem. It doesn't matter what that is today for us. And just know that like our answer at the end is low, right, on this graph. So what we did is we worked with Amazon, AWS, IonQ, and AstraZeneca. And on the IonQ machine and on the IonQ machines run through AWS Bracket, they ran a VQE, a variational quantum eigensolver. That's one of those hybrid quantum classical algorithms to find a starting value that would seed a classical algorithm with a better starting point than like a random solution, and then run the classical algorithm to actually get the minimum value that they were looking for. So here, only part of the job was given to the quantum computer, and that part of the job was essentially find a good starting place. Once we find that good starting place, then we'll let the classical algorithm take over. And I just want to emphasize that point is that many quantum problems that are going to be, lead us to advantage are such that the entire job isn't sent to the quantum computer, but we're still using all of the classical techniques and AI that we have available to really push the problem to a better solution than we can currently have with just using classical compute. And this is just an example of two things on this slide I want to illustrate. One is that we are and I mentioned it earlier, creating AI models to help with calibration and error correction. So our Ising calibration model and our Ising decoder model. These are open source models. They're available for free online. You can look them up and see how they were trained and everything. You can even, if you're interested in calibration, I know that's not the topic of this year's summer school, but if you've heard about it and you want to play around with it, we have an Ising calibration agent online where you can ask it questions about calibration. If you can take your calibration data, if you happen to have some, and throw it into that Ising model, and it will help you do the calibration of your quantum circuit or quantum hardware. This was just a really brief introduction into accelerated quantum supercomputing and Q2Q. And we have a lot of educational resources out there for you. And I want to emphasize that one of the things we did with our educational resources is that we tied them to the jobs that the industry is currently facing, right? The industry is trying to build better quantum hardware. They have to do simulations on that. So we have a whole series of notebooks on dynamic simulations of the quantum hardware. Even if we build less noisy quantum hardware, we're going to need error correction and calibration and control. So we have error correction modules, and we also have a new module on calibration. And in order for some of those error correction strategies to even work, they use AI, and we need data to generate that. So we do have actually working with Niels Bohr Institute, they've created a course on large-scale simulations of open quantum systems that's very helpful for creating and generating synthetic data to train AI models. And we do have like a quick start to quantum. If you just want to know how do you simulate quantum algorithms, we can go through that notebooks series, starting with the very basics and then moving up to understanding how simulation works with our simulation module. And then finally, one of the algorithms we're going to be looking at today, one of the tutorials we're going to be looking at today comes from our series on looking at quantum algorithms, not just the quantum algorithms that show up in the textbooks, but actually taking those textbook examples and pushing them into where real researchers and industry are using them. And that's not to say that they use those algorithms out of the box. They have to adapt them. There are limitations to those algorithms. They have to adjust for those limitations. And we discuss that in our algorithm tutorials as well. And so if you're interested in learning more, I'll put this QR code, you'll have the link to it in your learning platform, but it'll also show up at the end of the presentation as well. Okay, so let's get started with some interactive tutorial on an optimization problem. I'm going to leave this slide up here for a second so that you can grab that QR code to open up the notebook in Google Colab. You also have that link in your learning platform likely, if not right now, it will be there after the talk. And so that you can follow along. Otherwise, you can just watch the slides and the presentations and go to that notebook later. So I hope that just talking here a few minutes gives you enough time to grab that screenshot. We're going to be working on the max cut problem. The max cut problem is a nice way to introduce a quantum optimization problem that doesn't require a lot of background knowledge. That's why we chose it. We didn't choose it because it's going to lead to quantum advantage, like, you know, in the next decade or something like that. It's just that this is a problem where we have a really great classical algorithm that solves it, and there are also quantum algorithms that, you know, can also solve it. Maybe not as efficiently as the classical algorithm, but nonetheless, we introduced this from a pedagogical point of view, as opposed to being some like killer application, right? So I just want to level set the expectations of this. It's really to demonstrate the QAOA algorithm, demonstrate some pitfalls of the QAOA algorithm, and also demonstrate how AI is helping us to improve the QAOA algorithm to become even more performant. Okay, so I hope that was enough talking. The max cut problem is a problem about graphs. For this session, what we mean by a graph is a set of vertices or nodes. These are the circles connected with lines, those edges. So this is a graph, and this is the same graph, just a different coloring. And what we're interested in these graph problems is coloring the vertices, so coloring the circles with two colors, in this case, green or gray. And our goal is to find a coloring of the vertices that has more edges between vertices of different colors. So you see here on the left, we have 3 edges with vertices that have opposite colors. And so we call that a cut. A cut is the number of edges, or a cut is the edges between vertices of 2 different colors. In this case here, our cut has a size of 3 because it has 3 edges in it. And on the right, we have another coloring of the graph. So same graph, just different coloring of the vertices. And we get many more edges that connect vertices of different colors. In this case here, we get 5 edges that connect the vertices of different colors. And that's the best we can do actually for this graph. So this is called a max cut. And our goal in the max cut problem is to identify a coloring of the graph that gives us the max cut. So the one on the right here would be one solution to this problem. There are many solutions. If we swap the green colors for the gray colors, we'd get another coloring of the graph that would also be a max cut. We have the same cut edges, just the colors would be opposite. So it doesn't have a unique solution. So this is an optimization problem where we want to maximize the cut of a given coloring. It's a hard problem because the number of colorings that you have to sort through to find the max cuts is exponential with the number of vertices. So in this graph here, we have 5 vertices. So we have 2 to the 5 different colorings of this graph, because each vertex could have 2 different colors. So it's 2 times 2 times 2 times 2 times 2, 5 times, if I said that right. So that makes it very difficult to solve classically, naively. So just to make sure that we're all on the same page about the max cut, I want you to think about this for a second. We want to find a way to color this graph with 2 colors to find the most edges between vertices of different colors, to find the max cut. I've given one coloring here that's not great. It only has 3 edges in the cut. So could we adapt this? Can we change this coloring in some way to make it better? I'll give you just a minute to think about that. I know we don't have a chat function, but I want to give you time to think. What color would you change on this graph? What vertex color would you change to add in an edge?
I can read out from the chat here.
Oh,
Folks
thanks.
adding in the live questions, yep.
Oh, did somebody submit an answer?
Someone said 6, yep. Folks are saying 6. I hear then 1, 2, 6, and green. Okay.
Yeah.
Change 4 to white. Okay.
Yeah, those are exactly right. So if we change 6 to green, we could add in the edge connecting 3 and 6. If we change 1 to green, we could add in the edge connecting 0 and 1 and 1 and 2. So that would give us 1, 2, 3, 4, 5, 6 edges. So the max cut of this problem is 6. Like I said, there's not a unique solution. You might have come up with another coloring, but I think we got an idea of the problem we're trying to solve. Okay, so let's go ahead and see how this connects to quantum computers. So in a conventional classical computer, bits are either a 0 or a 1. So if you wanted to talk about all the different possible colorings of this graph, you can think of a bit representing the color of a vertex. So you would have, in this case here, 7 bits, and the bit would be either 0 or 1 to indicate green or white. And so you would actually need, just for one coloring, you would need 7 bits. If you want to talk about all of the colorings of this graph, you would need 2 to the 7 bits. So in a quantum computer, though, you only need 7 qubits to store all possible colorings, because each qubit could be either 100% 0 or 100% 1, or it could be some proportion like 50-50, 0 or 1. So you can represent all possible colorings through a superposition of quantum states. So each vertex would be a qubit. The color of that vertex would be based on the qubit value upon measurement. And so if we gave each one of these vertices a 50-50% chance of being measured as 0 or 1, we would actually capture all the possible colorings. Let's see how that works. But before I want to, so to see how that works, we'd have like a quantum processor. We're going to put in classical information. In this case, the classical information might be the structure of the graph. And then we get out, remember how quantum computing works. We get out from that quantum computer a probability distribution, because we run the quantum algorithm once, we measure it, and we get some answer. We run the quantum algorithm again, we measure, and we get maybe a different answer or maybe the same answer again. So in order to get out that probability distribution, to understand the quantum state at the end of that process, we have to sample or run this quantum algorithm over and over and over and over and over again to get that probability distribution. And so how that comes to play in our problem, instead of looking at the graph of 7 vertices, let's just look at 3 to make it easy. So let's look at this triangle here. To capture all the different colorings, what we're going to do is put each quantum qubit into an equal superposition through the Hadamard gates. And so when we run that, we get an equal probability of getting all zeros, of getting a 1, 0, 0, getting a 0, 1, 0, etc. So every time we run this algorithm through, we're going to get a different coloring of that graph with equal probabilities. In this case here, each coloring of this triangle has a 12.5% chance of being sampled when we run that quantum algorithm. In this slide, there's a lot of information how we essentially encode colorings into qubits, but also it has the CUDA-Q programming language here, so you can kind of see how things happen in CUDA-Q. We'll be working through this in more detail later, but this QR code, if you are interested, you'll have links to these things later. You can play around with drawing in a circuit and see how it translates into a quantum CUDA-Q Python code and how you would execute it. And there are different modes of execution. We'll be mostly looking at sampling today. Okay, so how do we solve the max cut problem? We can store all possible colorings in quantum state by using Hadamard gates, but they're equally likely to show up. And some of these colorings are not great for this triangle. For instance, the all gray coloring where all the vertices are gray, or the all green coloring where all the vertices are green, has a cut value of 0. That is not a max cut. So we don't want our quantum algorithm to produce an equal probability of all coloring showing up. What we want to do is we want to add some gates to the circuit so that we amplify the good colorings and we dampen the probability of getting one of the bad colorings, like the all 0 or the all 1, the all green or the all gray coloring. And so to do that, we need to figure out what gates to put into the quantum circuit. So in the app here, and this is part of that Jupyter notebook. So maybe I'll switch over to the Jupyter notebook just now so that you can see where this shows up in the Jupyter notebook. So I'm going to stop sharing this and I'm going to share the Jupyter notebook. So at the top of the Jupyter notebook, right, there's a lot of stuff. I'm going to scroll down to where we're at. I've been talking through most of this. There's the picture we had on the slide, and we're coding that graph in. I'm going to scroll down here to picture, sorry. All right, there's more room. Okay, so this is where we're at in the notebook if you want to follow along. So we put the 3 qubits in equal superposition. There are going to be some quantum gates that we're going to add to the circuit. This is called the QAOA circuit. The structure of it is not so important right now. If you want to learn more about it, we do talk about it in this notebook and some other notebooks, but you can just say that we're going to add some quantum gates, some rotations of these qubits, some entanglement of the qubits. And the idea is to break out of this equal superposition. You can see here, if I randomly sample the circuit here with just the Hadamard gates, and all of these gates have a rotation angle set at 0, so they have no impact. If I measure it, I might have a good probability of getting a bad coloring that has no cuts. And I have to maybe measure a couple more times till I get a good coloring that is a max cut. And the max cut of a triangle just has 2 edges. That's pretty simple. So what we need to do is we need to add these gates. We add some rotation angles. We have two rotation angles we can play with, an alpha and a beta. Ooh, and you can see that as I move them, the probabilities change. And I actually got really lucky here. The probability that I got a good cut went up to 96.5% from what it was previous when they were both zero, which was 75%. See here, there's equal superposition. 25% of the time, if I sample, I'm going to get a bad cut. If I add these gates and add some rotation angles, I could amplify the bad colorings, which is not good, or amplify the good colorings, like here. Now I'm at 87.8. I'm a little bit better. Maybe I'll get a little bit better. Nope. So you can see this is kind of a tricky problem. Oh, there we go. Figuring out what angles to put in there without running the code to figure out what those probability distributions is. But that's the goal, is to figure out what gates and what angles do we have to throw into your quantum circuit to amplify the good coloring so that a high percentage of the time you get the max cut. In fact, you can push this up to like 99.9% with the proper choices of alpha and beta, and you can kind of play around with that. But we're doing this sort of a brute force way, and brute force is never great, right? So there are other approaches beyond brute force, and this is where QAOA comes in. So what we just did above is we had a graph. We created the QAOA circuit with the parameters alpha and beta, and then figured out the max cut and saw if we got a good value or not, if we got a good probability of reading out a max cut. And if we didn't, then we changed the alpha and beta values by hand. And we repeated that until I got a good probability distribution like the one here, where we had a high probability of sampling a good cut. Every time I sample, I'm getting a good cut, except for in the rarer case that I might get the all green or the all gray, because those probabilities are really low now. Okay, so I was picking those alpha and beta by hand, and this is where the classical algorithm comes in for QAOA. We run the quantum circuit with initial parameters. We see if we get a good answer. If we don't, we send that information to the classical optimizer, and it gives us new values for alpha and beta to try in our circuit, and we cycle through this process here and then let the classical optimizer choose for us so that we're not just doing it randomly or by brute force. And this is an example of the hybrid quantum classical algorithm. Part of the algorithms run on the quantum computer, part through the classical, and we go through this loop many, many times. Now, each time we run through this loop, I'm computing the expectation value. I'm understanding what that quantum state is at the end, what that probability distribution looks like. To get the probability distribution, I have to run that quantum circuit thousands of times to generate that probability distribution. Because if I just run that quantum circuit once, I just get one coloring, right? I need to know the probabilities, so I have to run it over and over and over again. So each loop here in this algorithm requires thousands and thousands of quantum executions, which can be costly and maybe not really resource useful, and maybe too resource intensive rather. So we'll see about how we can remove this loop using AI later on. But that's the QAOA algorithm. Once we've got the alpha and beta values, then we just sample it and we get our coloring. We only have to really sample it once or a couple of times just to make sure we didn't get a bad coloring. So here I've done my QAOA by hand because I picked my alpha and betas by hand, and I sample it. Boom, I got an answer. I got a coloring that gives me a max cut just by sampling it once. After I've gone through that process of figuring out what are the alphas and betas that make the circuit amplify the good colorings. So that is a description of the QAOA algorithm, and there's more information about it if you wanted to read more in this notebook to get some of the terminology and the mathematics. This is what the QAOA circuit looks like. We put all the colorings in equal superposition, and then we code the graph, because the graph structure is going to be important, into some entanglement gates called the problem kernel. And then we mix things up with some rotations around the x-axis with another parameter beta. And then we repeat this circuit structure several times, 2 times, 3 times, 5 times, whatever. Each time we use different parameters. So instead of just picking an alpha and beta, you might have to pick an alpha 1, beta 1, alpha 2, beta 2, etc. So that complicates that optimization loop. So here's the entanglement that gets connects those gates. This part, like I said, is not very important for today's lesson, but is there for you to learn more about QAOA. So how do we code it? Well, the first thing we have to do is we have to generate what we call the cost Hamiltonian. In this problem here, we're trying to maximize the max cut value. So the max cut value is our is what we want to maximize. QAOA and all of our variational algorithms work on the idea of minimization. So we're just going to minimize the negative max cut and code that as an expression, and the mathematics for that shows up earlier in this notebook if you're interested in that. But the great thing about CUDA-Q is that in CUDA-Q there's a function called solvers, or there's a library called solvers, and inside it is a function called the get max cut Hamiltonian, and you put your graph into that as an argument, and I've got the graph coded already in this notebook, and then you can generate that Hamiltonian. I did not execute all the cells above, but if you did, the cell would execute and it would print out that Hamiltonian. Okay, and so then to run, the nice thing about this, for running this algorithm here, this flow chart, we actually don't have to put the quantum circuit in by hand. We don't have to code it in by hand, and we don't have to code this optimization loop in by hand either. There's one function that does all of this for us. All we have to do is create the graph, which I've done earlier in this notebook for you. We have to type in the cost Hamiltonian, which the solvers library has a function to get out the cost Hamiltonian for max cut. Then we'll have to initialize some parameters, and then we just call another function to do this entire loop. And then once we've done that, we can sample the circuit and get our result out. Just so that I can show you, let's go ahead and execute these cells here to make sure I get the graph loaded. We can solve it classically by brute force. Let's see, go ahead and do that. We saw the max cut value is 6. We figured that out earlier. These are just interactive widgets, so we don't need them because we just did them. There's our QAOA. Okay, so now we are ready to run the QAOA algorithm. So we have to get the max cut Hamiltonian and print it out. It looks like this expression here. Again, the math isn't important for today because we only have an hour, but if you want to learn more, it is in the notebook. And then we're going to create a function that runs, because we'll repeat this on other graphs later in this notebook. We'll create a function that takes in as input a graph, the number of layers we want in our QAOA circuit, and then some random seed just for reproducibility. And so we will get the max cut Hamiltonian, and this mapping here is just relabeling the nodes of our graph in case our graph was labeled with some strange labels besides 0, 1, 2, 3, 4. Maybe you only used even numbers on your graph. This would take care of that and make sure that it's properly labeled. So you plug your graph into your get max cut Hamiltonian like we did above, and then we have to set the number of layers that we have. Each layer has 2 parameters. So the number of parameters that we want to optimize, the number of alphas and betas that we have to find the optimal solution is twice that. We set a random seed so that we can reproduce the answers here. And then we set some initial parameters, and we're just going to pick an initial guess, some random rotation angles. And then we call the solvers.QAOA. So in the solvers library, QAOA is a function. It takes as input the Hamiltonian, the number of layers, the initial parameter values, and then a choice for your optimizer. There are lots of choices you can choose for the classical algorithm that runs that tells you what alphas and betas to pick. And we just choose Kabalia for this example here. And then we can run it. I execute it. Yeah, and we run it and nothing happens. Why? Because we're defining a function. All we do is define the function. So nothing has happened. If we want to actually run it, what we're going to have to do is, and this is one of the cool features about CUDA-Q. CUDA-Q works and maybe it was implicit in some of the slides earlier, we work with any type of quantum computing hardware, whether it be transmon superconducting qubits, trapped ions, or neutral atoms. And we also can run GPU simulations or CPU simulations of quantum circuits. So what we do at the beginning of a code is we set the target. We tell the computer where it's going to run this quantum part of the algorithm. And it could be on a CPU like we have here because it's just a small problem, or it could be on a transmon superconducting qubit or on a trapped ion. And we would just change or on a GPU, and we would just change this target depending on what physical device we want to run this code on. So the cool thing is that your quantum code here doesn't change. You just have to point the computer to the right device to run that quantum code on. It runs on all the different devices. So I'm going to run that function I just defined, QAOA, for the graph. I'm going to put in my sample graph. I'm just going to do a layer count of 1. I'll get out the results of that and store them as colors on my graph. And I can see that I found my optimal parameters, the most probable outcome of that graph, and the cut value here, which is 4, which isn't great because the optimal solution was 6. But this is where we can maybe make a modification and change the layer count. Instead of it being 1, if we increased it to, say, 3, we put in more gates and more parameters to optimize and run it. We see that we have more parameters to optimize, but we get the cut value as 6. We get a better solution. That's one of the features about QAOAs. There's a mathematical proof that says you add more and more layers, you're going to converge. You're going to be more likely to converge to a solution. And of course, we can plug this all back into our graph to see what it looks like, what that max cut coloring looks like of the graph we had. Okay, so QAOA has some problems. The first is the initial parameters we picked were random. If you pick different initial parameters, you're going to get different results. So there's some people that have done research into identifying what are good initial parameters to use for QAOA. Also, you notice that we went from p equals 1 to p equals 3. We got a better solution, but we had instead of now optimizing just 2 parameters, we had to find 6 parameters to find the optimal rotation angles, right? Here are all the 6 parameters here. What that does is it causes, if you think about maximizing and minimizing a function, if your function it looks like a mountainous range with high peaks and low valleys, you can find those peaks and valleys very easily. But if your function is very flat and just has very minor fluctuations, you might get stuck in a region of the graph that isn't the maximum or minimum because you're just moving around locally on these little tiny local minimums and maximums. Or maybe you're not moving around at all because you're at kind of a flat surface. And so as you're changing the different alphas and betas. So that's called the barren plateau problem. As you increase the number of parameters that you're trying to optimize for, the chance that you hit one of these barren plateaus and you don't end up finding the maximal solution increases. And so that's a problem. And then even with good parameter values, good initial parameter values, at the very end of the day, you have to sample this circuit thousands and thousands of times each execution loop. So this is very resource intensive, and right, so we have to find better approaches to this. And also the circuit structure is very, very deep. As you increase the number of layers, you have lots and lots of gates. And if you know things about error correction and noise on quantum hardware, the more gates you have more likelihood of noise to interfere with your solutions. And so having shallower circuits is better for the noisy hardware. Having deeper circuits becomes problematic. We can't just say P equals 100 and hope that it runs well on our quantum computer. So coming up with maybe a more efficient circuit structure that uses less gates would be a good idea. And that's what we're going to talk about next, is called adapt QAOA. Okay, yeah. So that next section, part of the code, just shows you how you can. We use the Q2QX functions to code that all up. But if you really wanted to code that circuit from scratch, you could do so by using our Q2Q. This is where it is. All right. Our Q2Q circuit notation. So to define a quantum circuit from scratch, you use @Q2Q.kernel and define a function. In this case here, I've given the function name kernel QAOA, problem 1. And that function can take in input. Maybe it takes in the number of qubits. In this case here, the Hamiltonian, that's going to determine the problem part of the circuit. The parameter values, the alphas and betas, I called them thetas here. The number of layers of the QAOA circuit. The first thing you do is you define a vector of qubits called Q2Q.qvector. So in the maybe we have 3 qubits if we had a 3-vertex graph, or in this case here, we'll have 7 qubits because we have a 7-vertex graph. We can apply gates to either 1 qubit or all of the qubits. So here I applied a Hadamard gate to all of the qubits. And then I'm going to apply the problem gates and then maybe rotation angles. And we give the angle of rotation here by a parameter value. And then the qubit that we want to apply that to, we can think of, if we just want to apply it to 1 qubit as opposed to all of them, you use the list notation. So qubits bracket j tells us to pick the jth qubit and apply that rotation angle to it. So that's kind of how you would code everything up from scratch if you were interested in that. But we have it all in a library, so that's kind of not necessary unless you wanted to get your hands dirty with that. So that's that part of the code just walks through an alternative way to code QAOA. And we talked about some of the challenges of running QAOA, including the optimization landscape here. So if I'm trying to find the optimal parameters alpha and beta, this is really easy when I have high peaks and low valleys. But if I flatten this landscape, I might get stuck in a region like over here, thinking I'm at a minimum, but the minimum is way over here. All right, so there are a couple of ways. I'm going to skip this section here. You can read about it later. There's a couple of ways we can address the circuit depth, and one of them is through adapt QAOA. So the way this works is we've got like our quantum circuit, we put the vertices or the qubits in equal superposition. We've run maybe one layer of QAOA like we did above, and we get some optimal values. So then instead of just doing another layer of QAOA, it could be that just one or two gates here with a parameter instead of this entire circuit structure repeated would be good enough. Because what happens in some of the graphs, some of the edge connections are like once you've figured out the coloring of one qubit, the other or one vertex, the other vertex comes for free. And so the entanglement between those two qubits, once you've got it figured out, you don't have to like keep repeating that over in your circuit structure. And so what we can do then is test out different gates to plug into the circuit and see what effect adding that gate to that circuit has on the probability distribution. So here if I added this one here and I increase the angle from that gate not being there, so 0 is as if that rotation angle wasn't there, and then I add a little bit to it, you can see that my probability goes down if I add a little bit of that gate. So that's not a good gate to add. Maybe the single X one is. I start out with a probability of 97.6 and I want to add a little bit of rotation angle with that gate. I'm again going down. So that's not a good gate to add. If I do this gate and I add an entanglement, start increasing, you can see here, I went from 97.6 down to 97.3. That's not great. But if I add the Y0, Y1 entangling gate instead, here I start with 97.6% probability of picking a good coloring. And if I add a little bit of this gate, a little bit of a rotation angle there, I go to 97.8, 98%. So this is a good gate to add to my circuit. So I'm going to add that to the circuit. And the way that it works then is with a little bit more complicated graph here with 5 vertices. Open this up in a new window, show it better. I pick the gate I want to add to the circuit that's going to give me the most improvement. And then I'm going to have to find the actual angle values that will optimize it. And then I go and I pick the next gate that will show the most improvement. Whoops, that's not this one is. And then optimize those angles. And I repeat this process of adding a gate that gives me the best improvement and then optimizing for the angles that give me that improvement. I repeat this. It seems like a lot of work, but let's see what happens when we compare this to the standard QAOA circuit. So the green, this is our approach that we just followed for finding the max cut. Lower number is better here. You can see we went through several steps here and we got a cut value. But if I were to do the same thing with a standard QAOA with just 4 layers, it would take me a much longer time to reach that minimum. So this is a much more efficient approach. And the circuit that we have at the end of the day is less congested. It has less gates than the QAOA circuit. So that's adapt QAOA. It still suffers from some of the same problems as regular QAOA because it required a lot of sampling. At each stage, we added a gate and then we had to optimize those parameters and run through that QAOA loop over and over again, that optimization loop. But it gave us a better looking circuit than we would have found otherwise. And so this is where I'm finally going to talk about AI now. This is where AI comes into play. What we've done is we have taken and ran adapt QAOA on many random graphs, and that gave us training data, which we had to translate into tokens or tensors so that AI could, understand it. So we encoded those graphs along with their QAOA circuit or their adapt QAOA circuit and optimal parameters. That was the information that we coded and ran and used as our training data for our AI model. And very much the same way as you train a large language model to predict what word comes next in a sentence, we're looking at what block of gates is going to come next in a quantum circuit. That's kind of the idea that comes into mind. So we've trained this model that to take in as input a gate and output the final quantum circuit with all of the optimal parameters from ADAPT QAOA. So we import a new graph. We have our trained model, and it gives us a circuit and the optimal parameters. And once we have the circuit and optimal parameters, we just have to take one shot of that circuit and read out the results to get the optimal max cut, the final solution. So there's no more an optimization loop. Once we train the model, once we train the model, we no longer have to run through that optimization loop. We got the trained model that's going to pick those optimal parameters and the optimal circuit structure for us. And so we just have to run one shot of it. So we went down from taking tens of thousands of samples of the circuit through each one of those optimization loops and then run it down to just one shot of that circuit to get the final result, the final max cut value. Let me go back to so that's the notebook, and I will go back to my PowerPoint here. We went through all of this, or most of it. Yeah. Okay. So before we close, I know we just have a few minutes left. I want to just emphasize that quantum computing companies today and quantum computing researchers and industry are using high performance computing, GPUs, and AI in their work. And one of the reasons why we see that there are reports that there's a huge gap in the workforce of the number of people that are qualified versus our number of jobs that are open. And one of the reasons that the number of jobs open is so big is because the roles are unfilled because of lack of skills. And what we're seeing in the last year is more and more people, or more and more jobs are requiring experience with AI and generative AI in their work. And so what we've done is we've taken our curriculum and mapped it directly to the problems that people are working on today, directly to the job ads that we're seeing in industry today, and making sure that that curriculum aligns with that. So it's a little less theory, but it's more in with the AI and the practical computing. And so in the final minute here, I just want to say that if you have any takeaways out of this, I hope it is that for quantum computing to get better, to scale up, to get to useful quantum computing, we're going to need AI at every level, from calibration to error correction to designing better algorithms and better hardware. GPU simulation is key in that, and it's key in generating synthetic data for training those AI models. And we can't do this alone. Even if we have the better quantum hardware out there, it needs the GPUs to run with it, to do the error correction, to do the calibration, to do the hybrid algorithms that we saw today. And so there are some learning materials available for you today, including the notebook that we went through today, if you want to access that directly. And if you want to learn more about CUDA-Q Academic, there is a webinar available for you to watch. It is directed towards professors teaching quantum computing. Just a heads up, it's not more teaching you how to do quantum computing. It's letting you know what's available if you wanted to self-study.
Awesome. Thank you, Monica. Do you have time for a couple of questions as well?
Yeah.
Okay, great. Yeah, folks, please add your questions here. I did see some from one student. He asked, what is the largest graph size that current quantum hardware can solve effectively using QAOA?
Classical can solve bigger. Let's just say that. So the number of qubits is related to the number, directly proportional to, directly equal to the number of vertices for QAOA. So if you have a 10,000 vertex graph, you're not going to be able to encode that into a quantum computer unless you have one that has 10,000 qubits. And those qubits are noisy, so you probably need to use, if you want, to get any reasonable results out of this, you're going to need error correction. Error correction takes maybe 100 physical qubits and turns them into 1 qubit. So yeah, pretty much this isn't an example of like what we can do today that we can't do classically. Classical computing can handle a lot of these problems. There's an algorithm called Gomans-Williamson that's really cool, that gives you great approximations to the max cut problem. But yeah, and we can do simulations, right? We can run these simulations on our GPUs as well. You don't the quantum hardware is kind of behind on this particular example.
Okay, yeah, that makes a lot of sense. We had questions, and this is from a while ago in your talk, but one of them was another student asks, as we increase the number of layers or the depths P to get a better approximation, how drastically does the classical optimization overhead increase?
Yeah, a lot, because now every layer adds at least 2 more parameters. There are variations of QAOA where it might add even more parameters. And so the more parameters you add, the harder job the classical computer has in figuring out which parameters it needs to adjust for the next round of that loop. Yeah, and so this is one great example of why adapt QAOA is good because you're only optimizing like a handful of parameters at each stage when you add a new gate. Because once you've got those parameters fixed at one level, you never change them when you add the next gates in that adapt QAOA algorithm. You're only optimizing parameters for those new gates. And then the next stage, you're only optimizing the parameters for those new gates. So adapt QAOA kind of avoids that problem of QAOA.
Okay, very interesting. That makes a lot of sense. And then we have one other student that asks, how do you know that the QAOA has reached a global optimum and not a local optimum?
Yeah, you don't. I mean, this is this is one of the problems, right? I mean, there are things you can do, but yeah, that's one of the challenges of the barrel plateau problem. And so some people have approached it by like running a couple of QAOAs from different initial starting values to see if you're converging to the same thing or if you converge to different things. So that's one approach is to just try QAOA multiple times with different starting parameters and see, and so you're starting somewhere else in that landscape. Maybe you're going to avoid those local minimums and actually hit the ones you want.
Awesome. All right, we have a couple more questions now. So is adapt QAOA, is that an example of a greedy algorithm?
It sort of is. I mean, yeah, depending on how strict you want to define greedy, but like, yeah, you're picking the gate to add that does you the best at that stage. It might not be the best overall, but yeah, it kind of has that flavor to it.
Okay. Oh man, we have so many questions. Okay, folks, pause on your questions, but maybe we can take these really quick. So if you had access to fault-tolerant quantum computer today, would max cut be one of the most promising optimization problems for demonstrating quantum advantage and why?
Well, max cut I mentioned is we choose this for a pedagogical point of view. The applications of max cut are kind of boring. I mean, you can look them up. There are a handful of them, but we talk about this one today because it's an easy problem to state, and you can directly see how the qubits are encoding the information from the max cut, the colorings. So
Okay, that sounds wonderful. Since a single layer doesn't reliably work, going to a deeper circuit seems the obvious fix. But if deeper layers take longer runs and measurement is still probabilistic, aren't we just multiplying a slower circuit runtime by thousands of required shots? Doesn't this create a new scaling trap?
bingo, this is why we have adapt QAOA and GPT QAOA. Yeah, there are lots of problems to QAOA, and researchers are looking in all sorts of different ways and avenues of making QAOA more performant. And one of the approaches I talked about today was adapt QAOA and GPT QAOA, but there's a ton of research in this area, and there's a ton of other approaches addressing all the different issues that QAOA faces. So I guess the takeaway here you're getting is that these hybrid algorithms sometimes have limitations that often don't get talked about, and it's important to pay attention to them because that's what the industry is looking at. How do we make things more performant?
Right. Yeah, I would encourage a student. Yeah, definitely look into it deeper. I think this is a good question and, worth for you to think about its solutions. All right. This is a bit more general question, but large language, LLM models rely on vast open resources to optimize the next token prediction loss. In the quantum domain, we face a severe data scarcity challenge. So what strategies or inductive biases can we introduce to a GPT-like architecture to successfully predict the next gate and minimize a cost function with limited circuit data?
Well, that gets quite technical. There's a couple of things I want to say. One is we don't have to rely on the quantum executions. We train the GPT model actually with noiseless circuit executions on our GPUs. So we were getting high quality data matching the QAOA to the graphs, and we were running small enough examples that we could simulate them on the GPUs, and that was our training data. And then there are a couple of things. I mean, yeah, the research literature is going to go into more detail of it. That's kind of beyond the scope of like this presentation today.
Okay, but we will have Monique again on July 13th. So
yeah, I guess I forgot to mention. I'll give on July 13th, I'll be giving more of a talk about all the other things that we're doing at NVIDIA. We'll talk more about error correction. We'll be talking more about designing better hardware, not just the optimization problem we did today. And hopefully by then you guys have had some time to go through some of those notebooks and learn a little bit more about Q2Q.
Awesome. Okay, I'll let you end on this note. We have a lot of great questions, but I'll email them to you. And thank you for joining us today. Really wonderful to have you.
Yep, thank you. Bye.
Thank you. Okay. So thank you all. Really nice to see you, and hearts to you all, and see you on Friday.